So in the previous parts of this chapter, we looked at polynomial functions and their graphs. And what we're going to be looking at in the last part of this is rational functions and their graphs. And rational functions do all kinds of weird stuff. So there's a lot of things that we will need to take a look at here. So just a couple of reminders with our rational functions. The first is we want to be able to talk about the domain. This is not new. We've done this before when we were talking about functions. Remember that we have to restrict the domain if the denominator is going to be 0. So looking at this first one, I want to know when x minus 5 is going to equal 0 because that's not allowed. And that means that x cannot be 5. But remember, we don't want to know what x is I can't have. We want to know what x is I can have. So that means I can go from negative infinity up to 5. Then I have to skip over 5, and I can go on to positive infinity. So that's what that would look like. Number 2, don't forget we always have to factor this. So this will give me x plus 5, x minus 5, and that helps me see that I have 2 excluded values. So I can go from negative infinity to negative 5, from negative 5 to positive 5, and from 5 to infinity. So again, that stuff is not new. Number 3, this is not factorable, but I can still solve the equation x plus 25 does not equal 0. That would tell me that x squared cannot equal negative 25. Well, the only way that could happen is if x was imaginary, and that's okay. Imaginary numbers don't show up on a real number graph. So that means that negative infinity to positive infinity is my domain. Okay? So that's a little bit reminder about domain. The next thing we're going to look at is vertical asymptotes. So the graph of a polynomial, of a rational function rather, can have 3 types of asymptotes. And if you remember, an asymptote from Algebra 2 means the graph gets closer and closer and closer, but it never actually crosses. So I could have, for example, a graph that looks like this, and I might have a vertical asymptote here and here. I could have a horizontal asymptote like this, and I could have a slant asymptote, which means it goes sideways, something like this. So maybe I have a function that looks like this, and this, and this. I don't know, I'm just making that up. But that's how the asymptotes would work. It gets right up to that border, but it never actually gets there. So those are the 3 types of asymptotes that we are going to be looking at. So the first one is the vertical asymptotes. These are pretty easy. Now, this is just some notation on here of how to read these symbols. We won't use these a whole lot. But this symbol here, x towards a positive, this means if I look at a coming from the positive direction. So if I say that x approaches a plus, that means x approaches a from the right. So that would be here. I'd be starting from the positive side and approaching this way. That would mean a plus. If I was coming from the negative side, a negative, that would mean that I'm coming in from the left. And so, for example, the way we would read on this graph is as x approaches 0 from the left, f of x, again, that's y, approaches positive infinity. So just a little bit about that notation, what that's going to look like there. So the definition of a vertical asymptote is that the graph approaches either positive infinity or negative infinity as I come in from either the left or the right. That's sort of the technical definition. We just know it's that vertical boundary line that the graph is never going to touch. It's going to get close, but it's never actually going to get there. So the way that we find a vertical asymptote is that if f of x is equal to p of q over q of x, p of x over q of x. So that's some sort of rational function. But here's the important part. P of x and q of x have no common factors. That means that it is simplified. We have to make sure that we have simplified the rational expression completely before we get our vertical asymptotes. And remember that a vertical line is described with the equation x equals some number. That's what the graph of a vertical line looks like. And so that is how we determine our asymptotes. So the first step for all of these to figure out what our vertical asymptotes are going to be is going to be to simplify these expressions. So I want to start by factoring. I get x over x plus 1, x minus 1. That's a difference of 2 squares. Nothing cancels out here. So that means that I get an asymptote at x equals negative 1 and x equals positive 1. And again, those are coming from here. Take the opposite, just like we always have been doing. Set those equal to 0 and solve for x, and those are the asymptotes. So when I look at my graph, it's going to be something like this. If this is negative 1 and this is positive 1, I'm going to have asymptotes here and here, vertical ones. Okay, this is the line x equals 1. This is the line x equals negative 1. So let's look at number 5. A little bit different because this is going to have some stuff that cancels out. So I have x minus 1 in my numerator, and then again I have x plus 1, x minus 1 in my denominator. Here, these cancel out, so I'm just left with 1 over x plus 1. It is only here that I get my vertical asymptotes. So this graph is only going to have one vertical asymptote, and it's going to be at x equals negative 1. So I won't get that second asymptote there. And then here at number 6, this is kind of similar to the domain question. I get x minus 1 over, this doesn't factor, x squared plus 1. So that doesn't simplify. And remember, if I set this equal to 0, I'm going to get imaginary solutions, which is not possible on the real number plane. So this one has no vertical asymptotes, and we can call those VAs. I think that's pretty common. Okay, so that is how you get a vertical asymptote. Simplify the expression, find where the denominator would equal 0. Now, what about those factors that we canceled out? Because remember, when we did our excluded values before, we did before we canceled. Same thing with the domain. So for number 5, even though my asymptote is only at negative 1, positive 1 is still excluded from the domain. How does that happen? Well, that is how we get a hole in the graph. So a value where the denominator is 0 does not always result in a vertical asymptote, because if it cancels out, then it doesn't give us an asymptote. But it does give us a hole in the graph, and it's important that you know that, because you will not see the holes in the graphing calculator. So the way it would look on a graph, for example, if we look at that middle example where I only got one asymptote that time, I'm going to have my dotted line asymptote here at negative 1. And let's say that I have some sort of graph like this. I don't know what it looks like. I'm just making this up. But this hole right here would happen at positive 1. We literally have a little open circle in the middle of our graph. That comes from the factors that cancel out. I don't get an asymptote, but it's just that one value for y that doesn't ever happen. Okay? So that is how we determine the vertical asymptotes.